The joys of live streaming. We had our share of technical difficulties this morning to get the show going, so we started a little bit late because of those technical difficulties. But there's always workarounds for everything. It's just a matter of figuring out what they are. Hello, everyone. I'm Tom Ballard, the Groundwater Guy, here presenting Groundwater Talk Live, and today we're going to talk about some groundwater news that I thought was interesting. So we're going to talk a little bit about deep groundwater and some research that's been done on that, and of course the drought that's gripping the Midwest and certainly the West certainly is continuing to have effects. So we're going to talk a little bit about some things there, and then I got some interesting stuff too, that some free groundwater books and some other stuff that I thought I'd share with you that's interesting and outside the ordinary. So let's dive in a little bit here. First off, let's talk about. I would appreciate any comments, likes, shares. It all helps with the algorithm to get the word out there on the show. We're building up subscribers, and I really appreciate everybody that subscribes. That helps me a lot, and we're trying to broach the 100 subscribers mark, which is kind of a milestone. So all your likes, comments, and shares really help in that regard. So I appreciate any of that stuff. And if you comment on the video, I will certainly I always reply back. So you're going to hear back from me if you leave a comment. So, and I appreciate all those comments. Thanks very much. And so let's talk today. We got a number of things going on out there. The big news, of course, is the drought that's going on and how it continues to impact the West, particularly California. And California is really in the news, but you also got a drought in the Midwest too, and we'll look at that here in a little bit. But first, I want to talk a little bit about there's some interesting research that's been done recently on deep groundwater and how pumping of deep groundwater actually draws contaminants down from shallow groundwater, and generally what we see when we're out drilling and looking at contaminants in wells is we see that a lot of the shallow groundwater, because it's surface water infiltration, picks up a lot of contaminants, especially things like nitrates. Total coliform is certainly an indicator of surface water impacts in your well. So we see that, but there's been some research done recently that I want to talk about here, and let me move over to my browser so I can share this with you. Where are we at here? Okay, let me blow that up a little bit here, see if I can do that. So this is it's an interesting title, Slurping Up Groundwater, but really what they're talking about is the summary here is researchers find that pumping draws young groundwater to new depths, potentially with contaminants in tow. And like I said, we see a lot of contaminants in shallow groundwater, especially things like nitrates. And so pumping the deeper groundwater can actually, this research is showing it can actually cause some of those shallow water contaminants to get into deeper aquifers. And we know that's true empirically, but they've done some research to show how that actually happens. So there are some, and they talk about how old your water is and this type of thing. It's true that deeper groundwater, shallow groundwater is going to be immediately impacted by precipitation. That's where that comes from. But deeper groundwater is going to take a while for that water to percolate down. And I got another illustration here. After we get through this, I'm going to show you how that works actually. Well, let's look at that now actually. So let me show you that. So this is basically how it works. You have your shallow water. You have a well that may be tapping that shallow groundwater. That's going to be recharged fairly quickly from precipitation. So you can see here that we're looking at days or years of time frame for that water to get down to those levels. So that's going to recharge fairly fast. And when we talk about managed aquifer recharge. We're talking about two things sometimes is artificial recharge as opposed to natural recharge. We're talking about either spreading basins that'll affect the shallow groundwater table or injection, which is going to affect the deeper groundwater table. So if we're looking at these deep aquifers, which are going to be down there, and the whole theory is we're looking at an unconfined aquifer up above. That's going to be immediately impacted by precipitation. And then you're going to have maybe a confining bed, which is going to be a clay, generally assumed to be impervious. Well, we know that isn't necessarily true. So down below that, we have what would be called a confined aquifer. That's going to be an aquifer that's under pressure. And then you might have another confining bed, another confined aquifer below. As water circulates down, it will go through these confining beds very slowly, albeit, but still penetrate through. So it may take centuries or millennia to get down to these deeper aquifer zones. Now, the problem here, and we're going to get into this. This is kind of the meat of the paper here that I'm discussing. The problem with this is that these confining beds are not necessarily continuous. It may be a bunch of clay beds in there that are interfingered that basically act as a confining bed, but water can still get through there. And these things are, even if it's a completely continuous clay bed, clay is not completely impervious to water. It's going to move through it very, very slowly, but it's not completely impervious. Um, so really what happens is most confined aquifers in actuality, if you look at them, are probably semi-confined aquifers that for the most part act as mostly as confined aquifers. That's probably the easiest way to explain that is you're not going to have regionally, unless you get in some areas in California where you have the Corcoran clay, for instance. But most places are these confining beds are going to be a series of clay beds that act as one, and they're not necessarily continuous. So water can still work their way through, but it works its way slow enough that it acts as a continuous confining bed for the most part. But just keep that in mind. The reality of geology is that most of the time when we talk about aquitards, aquicludes, and confining beds is they're probably not really going to be the definition of an aquiclude, which means it would keep out everything. That really does not exist in nature except under very rare circumstances. So we're really looking at these confined aquifers. For the most part, can be considered semi-confined that act as confined aquifers. So with that background, let's jump back to our story here and kind of look at this. So they're talking about the age of the water, and obviously the water in these deeper aquifers is going to be older water. And they look at this as saying right here, we usually think deep groundwater is safe from the contaminants found closer to the Earth's surface. However, intensive groundwater pumping is pulling recently replenished groundwater to deeper depths, potentially pulling contaminants down too. Well, this is only going to be possible if your confining beds that confine these deeper aquifers are not true confining beds or true aquicludes that they'll allow the penetration of water and contaminants with that water. So they go on to say groundwater takes time to move about the subterranean world. And that is true, and it flows a lot slower through confining beds. So they're saying half or more of all the groundwater stored on the planet is rain and snow that fell more than 12,000 years ago. So that's some of that deeper groundwater we're talking about, taking thousands or even millennia to get down there. So generally, the deeper you look, the older the water generally is. So they did some research on this and sought to determine how pumping affects the movement of groundwater And to this end, they leverage a data set of concentrations of a rare form of hydrogen known as tritium in 15,000 groundwater wells across the contiguous United States. Now, tritium is important, and it goes on to explain this because tritium shows up in groundwater basically as a result of atomic tests or nuclear bomb testing that actually distributed tritium. And sorry about that. Um, and so this is this is I'm sorry, I'm getting a lot of interruptions here, so my apologies. So the tritium actually indicates the age of water because tritium concentrations in groundwater date back to the nuclear tests back in the 1960s. So if we're seeing tritium in groundwater, that water is going to originate in the 1960s. So this is really kind of what we're looking at here. So they use tritium basically as a tracer, and tritium is actually tritium is a heavy hydrogen isotope. And so that substitutes into water, so we can start looking at the age of water and get that break between the 60s and earlier than 60s. So that's what they go on to explain here. And so we can use tritium concentrations in water to identify recent groundwater, and basically after 1953 is really what the date is they use for that. So anyway, they grouped nearby wells into 74 aquifer systems. This enabled them to analyze tritium levels of groundwater at different depths throughout each system. And they used the measurements to calculate the proportion of each sample that was from modern precipitation. And their cutoff for old groundwater was any sample composed of less than 25% modern groundwater based on tritium concentrations. So then they looked to see how this metric varied across different depths within each aquifer system. And so, unsurprisingly, the percentage of modern groundwater tended to be highest near the surface and decline at depths. But the transition occurred varied across different areas. This is probably going to be based on how effective that confining area actually is. So this is kind of what we're looking at. So now they had an idea of how deep modern groundwater was through the systems they were studying. But they still needed something to compare it to, and and like we talked about, water takes more time to sink into less permeable layers like clay. So it just does not move through clay very fast, very low hydraulic conductivity. Um, so they used local geology to characterize groundwater movement, and looked at confining layers or low permeability layers. And so they looked at this, and then they coupled with the analysis of confining unit depths and the age of the groundwater they were looking at, and looked at the impact of excess pumping on downward flow of the groundwater. So they basically tested their hypothesis using statistics to account for the geologic variability, and even then, you're going to have to make some generalizations because it's very difficult. We don't have complete data sets, so you're going to have to make some generalizations. But the bottom line is they did find that there was a correlation between groundwater pumping and the depth that young groundwater reaches, even after considering an area's geology. So the effect of pumping from these deeper aquifers is actually drawing water down much faster than it actually moved downward through natural migration. So it accelerates it basically, and that probably doesn't come as a surprise. We see evidence of that out there, but this is actually a study that's actually got scientific data where they pulled all this information to check this stuff out, and so what they're calling this is pumping induced downwelling. And basically, the way that works, here's an illustration here. We can see you got the shallower groundwater up here, these deeper zones. In between, you're going to have these aquitards or low permeability zones, and this is going to be a confined aquifer. And you can see, just even in this illustration, the discontinuous nature of some of these zones, which means that water is going to find its way through these low permeability clay zones. So they say when you pumping induced downwelling might be something that could occur in theory, but they're actually showing through this study that it is actually occurring. So previous studies have uncovered pumping induced downwelling at local scales in Indonesia and California's Central Valley, and we do see evidence of this out there. Just empirically looking at the data, if you're getting nitrates in confined aquifer zones, then really the only place it could come from is shallow groundwater, and it may be drawn down through pumping. So that's generally been our conclusion. So this is actually backing up the data you actually see in the field. So groundwater transports dissolved compounds called solutes, and they mentioned nitrates like I just did. Nitrates are probably a really common example of this, and so some of the clays are actually going to pick this up. So the clays act as natural filters, but it is still going to work its way down there as we pump deeper groundwater. So they go on to talk even benign solutes and contaminants can pose a health hazard, creating chemical reactions and mobilizing other contaminants. So you get complex chemical situations in the groundwater at depth. So a lot of these things can really create situations. They cite another case here where dissolved organic carbon can cause arsenic-bearing minerals to release their arsenic into the groundwater. Generally, surface water is going to be more rich in organic carbon, and so surface water is going to impact shallow groundwater. You pump that down there, you're going to get the total organic carbon concentrations increase. In areas where you have arsenic-bearing minerals, it could cause excessive release of arsenic through that chemical reaction. So this is a real phenomenon, actually. Also, they talk a little bit about salinity at depth, and so you're actually pulling some of this stuff around. We do know that in the Central Valley of California, for instance, and here in Tennessee, that we see deeper groundwater actually has increased salts in it, and so you get salinity or high total dissolved solids in the groundwater, and your pumping can actually drag that around as well. So all these things, deep groundwater pumping, it sounds great because the water should be cleaner down there, but you can drag down contaminants from surface water. You can actually increase the salinity from the deeper groundwater. So these are effects that we really got to look at. We have to understand them. We have to monitor them, and pumping that groundwater does not come without a price. So that's an interesting story here. I think that we have seen empirical evidence out there that this is the case, and it's interesting to see a study that actually supports some of the conclusions we've been drawing where you see this happening. So that's that's one of the things we look at when we are out in the field, and we know a lot of times you're looking at where these contaminants are coming from, because sometimes we can modify wells to actually deal with the contaminants. So we really want to investigate and understand where these contaminants are coming from. So you could be fooled by the effects of the downwelling through deep groundwater pumping and maybe not totally understand what the source of these contaminants is. Certainly, if we see nitrates and surface water phenomenon in deeper groundwater, then we really um, then we really know that we're getting some effects from surface water. So the conclusion we draw is somehow that's getting down there, and the effects of the deep groundwater pumping actually can exacerbate that effect. So there you go on that. So let's look at some of the effects of the drought out there. Um, we're going to talk a little bit about the drought itself and some of the effects. Out in California, we got another one of these stories where a city's water supply is expected to run out in 2 months. And this is actually Coalinga, which is down in the southern part of the Central Valley in California. And they basically feel like they got about 2 months of water supply left. So they're actually looking to buy water because they don't have any. Coalinga generally gets because they have low quality groundwater out there. They generally get most of their water supply from surface water from San Luis Reservoir farther to the north, and but basically they've been cut off because of the drought, and the water's going elsewhere. And so one of the things that they're looking at is going back to groundwater, but because of the poor quality groundwater, this is a pretty tough issue. They'd have to do more treatment, and so they're going and they're really looking at the possibility of buying water, which is challenging because everybody's out there trying to buy water. The prices have pushed up, and so anyway, it was it's been something that they're fighting about water cutbacks and who gets to water their lawns and who doesn't, and there's always somebody that are going to violate the cutbacks. So anyway, they feel like they didn't shut down their businesses during COVID, and so they feel like the state is retaliating against them for that. It's probably just that the problem is nobody's getting their surface water allocations the way they should. These guys have been completely cut off. They probably just don't have the political power because they're a smaller town. So, and here's talking about groundwater. Their brackish groundwater has never been a reliable option. So before a canal was completed in the 1970s that connected Coalinga to a major aqueduct, the city relied on water delivered by train, which is interesting. So they were actually bringing in water on train, and Coalinga actually started off as a coaling station on the railroad. So they do have rail lines there, but bringing in water by train is expensive, even of itself. But the drought has really, making them question the survival of their city. So talking about the drought here and giving a little background on that, we've talked about that, but it is really a pretty substantial drought that is affecting everybody. Surface water deliveries are down. There's restrictions on groundwater pumping and new wells, but people still need water, obviously. So California started its year with the driest 4 months on record. And so a little bit background here, they do talk about San Luis Reservoir is farther to the north, about 90 miles north, and that's where they get their water from. But they're not getting that now. No allocation from that network this year. That's important. They say that municipalities and industrial users were limited to what the Bureau of Reclamation calculates as their public health and safety needs, at first in the history of the Central Valley Project, which dates to the 1930s. So clearly, there's no public health and safety need in Coalinga because they shut them off completely. So Well, maybe not. So they got 1,920 acre feet of water, a quarter of its historic allotment, and so they raised that to 2,500 acre feet, but they're still 1,000 acre feet short of what they need. So acre foot is about 326,000 gallons. Um, so they're looking at that they're going to run out of water by mid-September at this point. That hasn't quite happened because they're out there purchasing water, um, and this story has been circulating around for a while. I just got a hold of it, but it illustrates what's going on out there. And the point I really wanted to make with this is what's going on with the water market is they were looking at they used to buy water for $190 an acre foot. Now the water is being sold on the open market for $2,500 an acre foot. So they're looking at to buy 1,000 acre feet, $2.5 million, which is 25% of the entire city's budget. So this is what's happened with the water market, and kind of the point of the story is obviously scarcity pushes prices up. So you've gone from $190 per acre foot to $2,500 an acre foot, and I don't know when this $190 is from. The water prices have been creeping up for some time, but we're now looking at $2,500 an acre foot, which is really a substantial increase from where it's been at. So Coalinga is not the only one that that is in this situation, but this kind of illustrates what's going on. And my main point here was what's going on with the water prices. And they're looking at drought profiteering. People are making money from selling water, and pushing up prices. It's true, but supply and demand situations basically say that if something's a scarce supply, you can get more money for it, and that's just really what's going on here. So I don't necessarily know it's criminal, but certainly delivery costs have gone up as well, and so there's certainly some reasons why the price would go up, but that's certainly um, exactly what's going on with water and the price of water. So they're looking at how they can eliminate water use and some of the usual measurements and fights over who's watering your yard and who isn't. So it's so that's basically what's going on. Um, so they are. This goes on to talk more about some of the uses and some of the effects, but the point is they got substantially reduced allocations of water. The early part of the article said they didn't get any, but that does not appear to be true as I read through this again. But what I wanted to point out was really what's going on with the water markets here and the price of water. So. All right, another related story here is, and this goes back to the Midwest, is we're seeing the Mississippi River levels dropping too low for barges to float. So this is reminiscent of what's happening to some of the rivers in Europe, where the Rhine River and some of the Seine River. These rivers in Europe are too low for the barges to float. Major transportation corridors, the Mississippi River, a lot of barges go up and down the Mississippi River. The lower Mississippi, not enough water flowing through it because of the drought in the Midwest. We were talking previously about California. This is actually the Midwest, and just not enough water draining into the Mississippi drainage basin, which is really the largest drainage basin in the United States. And the water levels have dropped so low that these barges, which have a pretty shallow draft on them, are not able to float down the river and deliver goods. So you're probably going to have to look at alternative methods, shipping by rail and truck, which is going to be more expensive. Barge traffic is really pretty inexpensive, and there's a pretty good network. The Ohio River flow, the Missouri River, but a lot of barge traffic on the Ohio River into the Mississippi and down the Mississippi to the Gulf Coast. And so this definitely impacts our, getting down to our supply chain. This is another impact to our supply chain internal to the United States. It's not just stuff coming over from China, but it's our internal supply chain, and things aren't getting delivered, and the stuff that is getting delivered is going to be more expensive because it requires more expensive transportation. So drought effects that you don't necessarily think about is what we're looking at here. So water levels are down to that point where we're seeing that some spots the barges can't pass. So gauges in some spots reported the Mississippi's river stages measure water height normally used to evaluate flood conditions with negative values. So it's dropping down below the gauge. These gauges were actually installed to look at flood levels. So the water levels will actually fallen down below the measurement gauges is how low it's getting. So obviously, drinking water inlets. There's a number of water systems that pull their water from the Mississippi, and so some of these intakes are getting dangerously down to the point where the water levels are dropping below the intake levels. So we're seeing that water supply is being impacted as well. So water levels are becoming too low for the barges to pass, and this just basically goes on to talk about that. And I wanted to point this out as an effect of the drought that we may not totally think about sometimes, but that is certainly an effect that on our supply chain. It's going to make everything more expensive at a time when we're already hit with inflation. Now we get supply chain issues that are going to push prices up as well. So we're getting a double and triple whammy out here with the price of water levels that affect transportation and inflation. So bad stuff. All right, with some of these introductory stories on the drought effects, let's look at what the effects are actually looking like right now. And you can see, obviously the kind of reddish brown color, the brown, dark brown is really the most severe drought effects, and then you taper down to the red, the light orange, the yellow, and then the key is that the S is short-term effects, long-term impacts, and then short and long-term impacts both. So we can see that some parts of the country, like here in Tennessee, we're seeing the effects too. It's been unusually dry for Tennessee this year, so we're seeing the effects here. We're getting some short-term effects. We have gotten some rain recently, but we're really seeing the long-term effects in the West, all the way into the Midwest, into Colorado, Arizona, New Mexico, California, Nevada. Really long-term effects, and we're seeing short and long-term effects through a wide swath of the West and into the Midwest, into Texas, and all the way to the Mississippi. So if you consider our last story we talked about, here's the Mississippi drainage basin. So half or more actually of the Mississippi drainage basin, which covers really this whole area here, there's big parts that are in severe drought conditions. So you can understand why the water levels in the Mississippi are actually dropping. So some substantial effects here, and so just as comparison, we can compare these maps, and looking at our current map And let's look at, say a few months ago, August 9th, and we can see that we had the drought actually was a little more severe. The conditions were more extensive and deeper into Texas. Texas is kind of getting a little bit better. If we go back to, kind of the start of the summer, June 7th, this is kind of what it looked like. We were still having drought in Texas out west, but not so much out here. So we can see that the drought effects have actually spread. And if we go all the way back to, say, the beginning of February, this is what it looked like. So it was starting to ramp up, actually. Not as severe as it is now, but it was starting to ramp up. And I'm not sure how far back we can go. If we go back to 2021 and look at kind of our same time period in 2021, we can see that the drought was more in the west and on the upper west. Not so much in Texas. This year's actually spread to Texas and the Midwest. So if we go back 2 years and look, we can see that this is what it looked like. So persistent drought in the West. Texas and the Midwest has kind of been off and on, but it's been pretty persistent this year in the Midwest. But the drought in the West has been going on for quite a while now, and is really starting to substantially affect things. So that's kind of our look at drought conditions. That's it continues to, and it doesn't look like it's going to get any better. The conditions in Texas and the Midwest may clear up a little bit as we move into the fall and get some rain. So we're just going to have to monitor that. I'm not sure what the precipitation forecasts call for there, but that's really something we're going to keep an eyeball on, because we've seen that's really starting to affect and it's starting to creep out east as well. I was expecting we would get some relief from the hurricane. Florida did, I guess, but Florida's not in drought. But we got nothing from the hurricane here in Tennessee. Usually some of that stuff pushes up in here and we'll get some rain. And Tennessee is normally fairly rainy. Of all the states Tennessee borders on 8 states, and it tends to get be the wettest of all the states due to some of our natural conditions here. And it's unusual to go for a week without rain out here, and we've had quite a number of weeks without rain. We just got some, like 3/4 of an inch yesterday, so that helps, but it just sopped it all right up. So we definitely need more out here. So we're still in semi-drought conditions ourselves. So it is starting to push east as well, and that's certainly a concern as it grows and spreads. The West is really locked in a real problem that seems to be very persistent and does not seem to be relenting. We'll see what the winter brings, but if they go into next year with the drought conditions the same, it's really going to create some severe impacts. So we're going to continue to monitor that. All right, let's move on to some other stuff that I wanted to talk about a little bit. Yeah, one more drought story here. Talking about Owens Lake here, and let me shift this here. Yeah, this is another drought story, but talking about Owens Lake, which is it's a dry lake bed down in the eastern Sierra area in California. It's basically a dry lake bed, and so this article is actually talking about it does get water in there. It's really nasty water because it's a closed basin, so you get a lot of nasty stuff in there. But it does recharge the local groundwater. Unfortunately, the groundwater right next to Owens Lake has got nasty stuff, heavy metals, arsenic, things like that in there. So, but they're talking here about that you could pump water in there and recharge it. I don't know. There is Owens Lake and Mona Lakes, which is farther to the north, are what they call terminal waters because they are a closed basin. There's no outlet, so the water flows in there. It doesn't go anywhere else. They evaporate, so they're very high in mineral content because there's nowhere for things to go. So the minerals dissolve in the water. They flushes down, and it flows into these dry lake beds. And it evaporates, and the mineral concentrations of this water are very high. That seeps into the groundwater, makes groundwater fairly nasty in these areas. So, but it is an important part of the ecosystem out there. Without recharging the water, is that you're going to impact groundwater. You're going to impact a lot of the ecosystem out there. So they're talking about some schemes to actually rehabilitate Owens Lake and make sure that it gets water. I don't know how realistic this is, but it's just another drought story I wanted to throw out there to you. All right, so here's another story is that that I find this kind of interesting because we are here in Tennessee where rainstorms are pretty intense anyway, but they're saying rainfall is becoming more intense in most of the U.S. And I can't speak for Tennessee necessarily, but when we get a rainstorm, it's the Tennessee vertical rain. It's like standing in your shower. You can get 2 inches of rain in half an hour very easily. That is not that uncommon, and it just when it dumps, it dumps. You don't want to be out in it because it just floods everything and the creeks swell up. But this study here is actually looking at the fact is that we're getting rainstorms that are actually becoming more intense. And so for much of the United States, I don't know how this applies to the rest of the world, but it said when it rained east of the Rocky Mountains in recent decades, about 5% more precipitation fell. When it rained over the Pacific coast of Rocky Mountains, however, no intensity changes were observed. So this actually ends up contributing to the drought. So this is basically a drought-related story, but it's an interesting study because we know out east here we do get these intense rains, but it looks like it's actually the intensity is actually increasing. So they attributed, of course, this to climate change affecting the weather. Obviously, as everything is related to climate change. So, but it's. This may be a reasonable assumption. I don't know, but warmer weather may create some of these heavier precipitation situations. But it's basically good for the east because we're a little wetter. But they bounce it all over to climate change. But I thought it was just interesting that the rainfall intensity is actually increasing. So, and I kind of monitored ours here at our farm. We got a rain gauge out there, and it is amazing how much rain you can accumulate over a short period of time. So I guess that's becoming more the norm. So anyway, they analyzed observations with 17 distinct climate regions in the United States, and after analyzing data from 2 time periods across regions, they discovered that precipitation intensity, including rain and snow, had increased across much of the United States, particularly in the East, South, and Midwest. But Western U.S. not detected. So no opportunity for any of this effects to create relief from the drought. So, all right. So that's that. I wanted to move on to a couple last items that are really more fun and instructive. One is the Groundwater Project, and I find this very interesting because this is John Cherry started this with a few other people. John Cherry is pretty famous in groundwater circles, and he wrote kind of the classic book. Freeze and Cherry is the classic book on groundwater in the business. But they started this project that's basically free books online. You can just go to the site and download these books, and you can see there's quite a variety here. understanding hydraulic head, groundwater flow, water cycle, ground flow nets, groundwater storage and confined aquifer, um, groundwater velocity, isotopes, groundwater microbiology, karst aquifers, um, land subsidence, managed aquifer recharge, flow models, really domestic wells, electrical imaging for hydrogeology, um, large aquifer systems around the world, uh, and um, and then there's actually a book even on the Edwards Aquifer in Texas. So the classic books are here too. This is Groundwater by Freeze and Cherry. So that's our classic book. If you're interested in contaminants, especially dense non-aqueous liquids, solvents, basically in groundwater and cleaning them up, this is actually a classic book too. John Cherry was one of the authors on that. And then the classic book on analysis and evaluation of pumping test data. This is really the classic. If you're interested in anything about pumping test data, this is available here, and this is all free. Just come on here, download it. You don't have to give them your email address or anything. They actually have some children's books too, so that you can share. And then they have some more books in the works, so they're continuing to add to the collection. So some interesting ones that look like they're coming up here: stable isotope hydrology, flow and distribution of non-aqueous phase liquids, some more contaminant types of things, fractures and faults, some basin hydrogeology, geophysical logging, structural geology, applied to fractured aquifer characterization. This is really important if you're dealing with wells in bedrock. So I'm looking forward to these books coming out, and they probably have some more on the horizon too. Definitely bookmark this one. Go and download what you need, because this is all free information. So it's really a rarity out there. A lot of these books. Some of these, if you bought them, they're going to be, $100 books. So these are available for free. So mark that. It is gw-project.org. And you can go there, and a lot of interesting information, and download these books and put them in your online library. So that's interesting. And lastly, I kind of wanted to wrap up here on LinkedIn. Charlie Carner of WellJet, that they do well rehabilitation, and they use a high pressure hydrojetting method. They just came out with a new nozzle, and I wanted to, and they did a demo of this, and he posted this up on LinkedIn, and I wanted to show this to you. We've used WellJet; they work quite well. They can adapt this for various size wells, and part of the challenge with doing well rehab is getting through the screens out into the gravel pack and the formation. You need to have a lot of energy to do that. And hydrojetting is one way to do that. So we usually use hydrojetting in conjunction with some other methods. Obviously, you want to clean the screens up first so that the hydrojetting can get through. So it's going to be part of a combination method, but you can really see how high pressure and linear these jets are, which are really important, because applying that energy to get through the screens, to get out into the gravel pack and reach out there is really important, because so many people, when they do well rehabilitation, is they clean out the inside of the well and clean the inside of the screens, and they call that well rehabilitation. But that is not, because it's like an iceberg. Is you're only seeing what's inside the screens. The vast majority of the problem is going to be outside the screens, in the gravel pack, and actually extending in the formation, whether that's mineral incrustations, whether it's biofouling. That's going to be out beyond the screens. Very hard to see, but you got to apply the energy to get out there. This is one way to do that. So let me blow this up and apply the sound so you can look at this and really see what's going on. This is really pretty amazing when you look at it. Just an amazing video. See the nozzle WellJet. Um, you can find Charlie on LinkedIn or look up WellJet on the internet. They work all over the place. They're based in California, but they go all over the place and internationally too. And Charlie is a great guy to work with. He'll answer all your questions. So I'm giving them a plug here, but I just thought you'd be interested in seeing that nozzle test because it's pretty fascinating to me. So let's all right. So that's our show for today. Sorry for the technical glitches that I had at the beginning that got me going late, but you can reach out to me at tballard at Groundwater Guy if you got questions on groundwater, you want to discuss anything. Um, we if you're interested in being a guest on the show, I'd love to have you on. If you have, good information on water, groundwater, water systems, I'd love to talk to you. I have a book me page that you can book a session to come in here. So check that out and let me know if you want to be a guest. Um, we stream live. Where is my? Oh, wait a minute. There we go. We stream live to the Groundwater Guy YouTube channel and also on LinkedIn, so you can find us those two places. I have all my past shows on YouTube, so um, that you can find all the past shows. We have some interesting stuff there. Don't forget to subscribe to the YouTube channel if you want to be notified when I got new videos up there. Hit the bell, and that's our show for today. Thank you very much for watching. And